Okay, so let's see if you're following. If you just finished the last lecture, what is the electronic configuration for phosphorus? Phosphorus is right here. So answer is it's neon's configuration, then 3s2, 3p3. So this is the right answer. You can't. So 3p5. This is possible. It's an excited state. Um, writing magnesium like that, that's not proper. You only use the the noble gases. And this one is wrong. You can't have three electrons in an s orbital, and its s orbital is also lower energy. And this is the power of the quantum mechanical model. So we have valence electrons dictates electronic properties, and that means that the columns on the periodic table have similar properties, and sometimes referred to as family. So here's a picture of my family, although taken, oh geez, this is taken about 12 years ago at the time I'm recording this video. You can see I'm the fourth of five kids. I'm from the far right. And you can see, I mean, there is a certain family resemblance. There are my parents in the front. We're all kind of big and blonde. We're kind of the big blonde tribe. Here we even, dress similarly just for the sake of pictures. So we're all each individuals, of course, but we do have some characteristics. Like, man, I had more hair back then. Even then I was losing it. And here's my father, my brother, and my nephew doing copper, silver, gold. So there's a family here in that regards. But so the thing about the like, okay, copper, silver, gold, they're all very similar. I mean, like, well, if you look at my father, my brother, and his son, they look very different. What's going on here? Well, copper, silver, gold actually are very similar chemically. They're all very unreactive. So gold, of course, is the most unreactive, but copper and silver are fairly unreactive, and we use them for that property. They also conduct electricity very well. We have copper wiring for that reason. So then we have families. We call them families of columns. So alkalis, we talked about the alkalis, the first column, all have plus one charge, all very basic. Basic as in not acidic. Alkaline earths, they're also alkaline, but they're also less soluble than the alkalis. And the halogens, they all tend to have negative one charges. So the charges are from the valence electrons. So there's lots of properties here with that, with the electronic structure. Okay, so let's talk about periodic trends. And with the atomic radius, the general trend is that the radius decreases from left to right. You can see it gets a little wonky in the middle with the transition metals, but for this class, we're mostly going to talk about the S and the P blocks. And you can see that the radius doesn't change that much for the transition metals in the D block, but generally it decreases left to right. And what is the reason for that? Well, if you look at the alkali metals on the far left, they have an effective nuclear charge of +1. And then you move over to the halogens, they have an effective nuclear charge of +7. So the electrons, as they're moving, moving left to right, there is a stronger electronic charge, or a stronger nuclear charge, and because of that, the atom shrinks. The electron density is drawn closer to the nucleus of the atom. Similarly, going down a column, the atom is getting bigger, and it's just a bigger ball of charge there. So the s electron, so lithium has the 2s electron on the outside, sodium has a 3s electron. The core electrons shield it, so the outer electrons feel a smaller, less dense ball of charge. So because of it, the electrons just kind of blow up and occupy more space. So that's the reason. So the trends are going to the right, it decreases in size. Going down, the atom increases in size. You can see the general trend here that they do. In fact, it gets a little, transition metals gets a little screwy, but in general, left to right, it goes down. and that's because of the effective nuclear charge, as I've said. Okay, so let's use this logic. Choose the larger atom from the following pairs if possible. So start with carbon and fluorine. Here is carbon. Here is fluorine. Fluorine is further to the right. Therefore, so choose a larger atom. I'm sorry. Larger atom, carbon is the larger atom. Next one, carbon, do again, or germanium. So germanium is lower, therefore it is a larger atom. So nitrogen or germanium. So nitrogen is further to the right, germanium is lower. So both, nitrogen or, oh shoot, I didn't do aluminum. Sorry. Nitrogen or aluminum. Aluminum is further to the left and is down, so therefore definitely aluminum. And then we have aluminum or germanium. So which one is it? This one here, we don't know. It's ambiguous because germanium is further to the right, so it should be smaller. Aluminum is further up, so it should be smaller. So they kind of, we have conflicting rules here. So we're not entirely sure. Okay, and something I should also mention, diamagnetic means all electrons are paired. Paramagnetic means one or more unpaired electrons. And this has absolutely nothing to do with reactivity or electronegativity. We haven't talked about electronegativity. That is the attractiveness of the nucleus. So a lot of students try to combine these two concepts. They are not at all. So gold is paramagnetic. It is very unreactive. Fluorine is paramagnetic. It's extremely reactive. Calcium metal is diamagnetic. It's extremely reactive. Let's see here. Mercury is diamagnetic. It's very unreactive. So they have nothing to do with anything, just nothing to do with reactivity. So keep that in mind. Okay, so let's talk about magnetic properties for ions. And remember, with valence, electrons are taken from the highest and principal quantum shell first. So here, aluminum, its structure, do we have aluminum here? Okay, aluminum right there, it's neons. It's neons structure 3s2 3p1 by ripping off the top 3 electrons, it's going to be neons configuration 3s0 3p0, and neons is going to be 1s 2s 2p, and the electrons are going to populate as such. Everything is paired up. This is diamagnetic. Okay? And then let's do sulfur. Sulfur -2. So here is sulfur by itself. It's going to be neons configuration 3s2 3p4. Here's sulfur right here. 1, 2, 3, 4. And the -2 ion, it's going to be neons 3s2 3p6. And so we'll have, just to say, 3s 3p, and it'll be populated like so. And this is diamagnetic, meaning it will not respond to an external magnetic field. At least the lone atom and or ion won't. So iron +3, so iron as is, it's going to be, where is iron? Iron is right here. So it's argons, 4s2, 3d, 1, 2, 3, 4, 5, 6. So iron is argon, 4s2, 3d6. And so then the highest end first, so if this is plus 3, we're going to lose 3 electrons. It's going to be argon, 4s0, 3d5, which means we have 4s, 3d, 1, 2, 3, 4, 5. All parallel spin by Hund's rule, and this is definitely paramagnetic. Has all these unshared pairs of electrons. So iron plus 3 ion is very effective on an external magnetic field. So not surprising for you to hear that, I'm sure. Iron tends to be very magnetic. Of course, there's a difference between paramagnetic and ferromagnetic, but that's if you study more solid state physics. Okay, so this is, so remember, paramagnetic, one or more unpaired electrons, and has nothing to do with reactivity, but does have things to do with magnetic properties. And so next concept, students struggle with this one. This is known as isoelectronic atoms and ions. So we have sulfide, chloride, argon, potassium, and calcium ions, respectively. So if you look at these all have 18 electrons. And how does their size go? The size goes sulfide is the largest, followed by chloride, followed by argon, followed by potassium plus 1 ion, followed by calcium plus 2 ion. And why is this the case? Because they have the same number of electrons, so they're going to have the same electronic structure, but the positive charge in the center is smaller. So if you add electron density to an atom, what happens? The atom blows up. It gets big. The electron clouds don't like each other. The electron cloud expands. What happens when you take electron density away from an atom? The electron cloud shrinks. So, and here with calcium plus 2, you have those 20 protons there and the fewer electrons. That's a very tiny ion. It really sucks in there. So let's see if we can do this. Choose a larger atom or ion from each pair. So sulfur or sulfide. This has more electrons. It's bigger. Calcium or calcium plus 2. This has more electrons. So bromide and krypton. So bromide and krypton. They have the same number of electrons. So their periodic table. So bromide, -1, and krypton both have 36 electrons, but bromide has 35 protons, krypton has 36, therefore bromide is a larger ion. Does that make sense? Same thing here with those isoelectronic. Bromide and krypton are isoelectronic. Since krypton has more protons, it's a smaller, makes bromide bigger. Okay, so moving on, we have trends in the first ionization energy. So first ionization energy, this is the energy it takes to rip off an electron, one electron from the atom. And here is the trend. The general trend is when you go from left to right, it increases. If you see there is a shift in these ones here, but then goes away. For the first for periods 2 through 5, you have a, 2, 3, and 4. 2, 3, and 4 periods, this goes down. The reason for that is it's easier to rip off this electron from oxygen than this electron from nitrogen. And the reason for that is because the oxygen electron is paired up with the other one. So that's an interesting trend. But the general trend is from left to right it goes. Increases. Something to note with also ionization energy. So if you look, say you were to look at magnesium's ionization energy, the first ionization energy would be big. The second ionization energy would be relatively bigger. The third ionization energy would be huge. And the reason is because you'd be ripping it off from a noble gas configuration. So say you looked at potassiums, the first ionization would be small, the second would be very, very large because you're ripping it off from the noble gas configuration. Same thing with aluminum. If there's aluminum, it would increase, and then you would have a huge increase. The huge increase is when you get to a noble gas configuration. But let's go back to the first ionization energy. This is the first one. On the basis of periodic trends, determine which pair has a higher first ionization energy. So we have aluminum and sulfur. So which one has the higher? Sulfur is higher because it's to the right. Arsenic and antimony. Here's arsenic. Here's antimony. Arsenic has the higher one because it's higher up. Nitrogen or silicon. Here is nitrogen. Here is silicon. It is definitely nitrogen because it's to the right and it's higher. And then we have oxygen or chlorine. Here is oxygen. Here is chlorine. This one you don't know because it's ambiguous with the reasoning. Okay? Now moving on, talking about electron affinity. Electron affinity is the energy released when an element absorbs electrons. There, in general, is no periodic trend. There is an increase across a period, but I more or less disagree with this. This is my own personal belief because, so for instance, xenon has electron affinity, and xenon, that's weird because it's a noble gas. And some do and some don't. It's not a smooth trend. So I should write this, not a smooth trend. So it is, so size and first ionization energy is they tend to be very smooth trends. Electron affinity, not really at all. But it's in the book, I'll tell you. Metallic character, this is another one I think is stupid. But metallic character, I can see kind of the argument. The general trend is that as you move across a period, the metallic character goes down because chlorine is definitely a nonmetal, and sodium is definitely a metal, and aluminum is definitely a metal, and sulfur is definitely a nonmetal. And same thing with the going down a column. Nitrogen is definitely a nonmetal, and bismuth is definitely a metal. And then going down, arsenic is kind of in between. So I kind of see that, I get it, but it's not like you can compare. Does that mean that chlorine is a better nonmetal than sulfur? Is that more of a nonmetal characteristic? It's another not so smooth trend. So here's the general trends. So atomic radii, as you move down a column, it gets bigger, and as you move to the right, the size gets smaller. First ionization energy, as you go down a column, it's easier to rip off an electron, but this also makes sense though, because you have a bigger atom, and the electron is further away from the positive nucleus, therefore less Coulombic force, so it's easier to rip it off. And then as you go across the periodic table, the atom gets smaller, therefore the electrons are harder to rip off because they're closer to the nucleus. There's more of a Coulombic attraction. Electron affinity, it generally a little bit as you move across, but this is not a smooth trend. Same thing with metallic character. As you move down a column, it increases, and as you move across a row, it decreases. So it's this is saying that metals like to give off their electrons more. So, but it's kind of the opposite of first ionization energy of sorts. Okay, so done with periodic trends. Next chapter we'll get into is with bonding.